Sure, yeah, I'm very excited to talk about it. So just about the structure, I'm just going to introduce it. We're going to go over template Haskell a little bit because I'm not assuming you guys know much about template Haskell. There's a lot of usages of it, but I feel like people don't really write template Haskell. We're going to have some breaks. We're going to talk about the interfaces in depth and how it interacts with build tools. So we've heard a lot today about the importance of stable interfaces, right? We want our code to be resilient. We, especially as a corporate user, right, we use a lot of dependencies, and when they change, we don't want our code to break. We also potentially expose interfaces to other people, maybe internal teams, or maybe we publish packages, and we want those interfaces to be resilient too. And template Haskell is an interesting case study when looking at something like this, because it's deeply coupled to GHC. So there's kind of like an inherent instability here. GHC changes all the time, but we don't want template Haskell to necessarily change or break things. And by teasing that out, I think we can learn a bit about writing stable interfaces in general, but also it's helpful, obviously, for the important task of keeping template Haskell itself stable. So in this talk, I want to talk about like what the current state of stability is, how we can make it better, and also like this inspiration we can draw from template Haskell. So I first got involved with these things because I saw a discussion on the GHC issue tracker, and I just finished writing a library that used template Haskell, and I'd also just finished doing the like biannual work upgrade of GHC, and that's always a bit of a chore and requires changing things to deal with template Haskell. And I felt like things could be better. And so, yeah, I got involved. And now I've been doing this for a little bit over a year. I haven't been consistently doing it over a year. There's been lulls in my involvement. And I wanted to bring that up because I think that's very normal and natural. And I feel like people don't get involved in GHC or open source sometimes because they feel like, oh, I can't commit to this project. I only have so many hours in a day, and I might not have time every single week to work on it. And that's completely okay. And I think this project has benefited a lot from GHC's culture of communication. A lot of the stuff here is stuff that's actually been around for a really long time. People have been thinking about this and have been working on this, and they've written it down. So that makes my job a lot easier. I can just read the extensive notes in GHC, tickets people have written, design documents. Yeah, it makes my job a lot easier. And this work has also greatly benefited from discussing this quite a bit last year. I feel like ZuriHack last year was just a blur of template Haskell, and from frequent discussions in the Haskell Foundation Stability Working Group. And I feel like a lot of this stuff is kind of collating everybody's work. And a lot of the ideas here are that really. It's just, most of it is about planning and figuring out what actually needs to happen, because we all have a sense that template Haskell could be better, it could be more stable, but just kind of teasing out what specific steps we have to take and in what order is a lot of the work. And I feel like sometimes it's something we forget. And it's also work that is maybe a bit more accessible to people, right? You don't have to be a compiler's expert. You don't have to be this academic with a PhD. You just kind of have to figure out the relationships between things. And it's a bit like untangling Christmas lights, where you're just slowly working away at it, and eventually stuff clicks. And yeah, a lot of these ideas have been around for a long time, but we've just been blocked on somebody putting the time in and working on them. And that's also true of lots of areas of GHC. So I kind of just want to say, get involved with GHC. You don't have to understand all of it. You all only have to understand one tiny bit to make progress, and it's a lot of fun. Okay. And now moving back to template Haskell. Okay. Let's take a look at just like a brief overview of it. Let's look at it through some examples of usage, which I feel are more familiar, right? So a very common thing is lenses, optics, stuff like that. Type class deriving, maybe ASIN, 2JSON, stuff like that. We see quasi-coders, right? Like Yesod uses them quite extensively. There's those Shakespearean templates. There's also raw strings that, and like string interpolation, stuff like that. We have embedding static data. So it's like, I think if you've been around Haskell for long enough, you'll see some usage of this. It's a bit of a shame that this doesn't include much type template Haskell, which is a big part of template Haskell, which is a bit more of a recent thing. But yeah, people should write more of that, basically. So while usage of template Haskell might be familiar, I think template Haskell isn't all too familiar to people. So normal programs run at runtime, and in template Haskell you write meta programs. So a meta program has a part that runs at compile time, right? And why do you want to do this? You want to insert program fragments into your code that you're generating at compile time. You're looking at compiler state. Maybe you're looking at the definitions of data types to figure out how you're going to create that code, right? And that's basically what a meta program is. And this is like one way of doing something like that, but there's lots of other tools that people could use that interface with GHC in different ways. So like at one end, you have like preprocessors, and preprocessors don't know anything really about GHC syntax. They're just run on the source files. And in some ways that makes them quite powerful because they can just transform things in uncontrolled ways. But then you have to do all the parsing yourself. There's generics that are a lot more powerful, right? You know stuff about the shape of data types, but you're limited by the data types generics knows about, and also mostly for just deriving type classes and stuff like that. But they don't require running any user code at runtime. And then there's GHC plugins, which we've heard a bit about, which have complete access to the GHC internals, and that makes them quite coupled to GHC, so that makes them a lot more liable to break, but it also means that they're a lot more powerful. And they too require running user code at runtime. And template Haskell is coupled to GHC, but it's less coupled than GHC plugins, and more coupled than generics, so you can kind of think of it falling somewhere in the scale. So with template Haskell, you are dealing with GHC's syntax, and you are accessing the state of the compiler in some way, right? For looking up at all sorts of information, maybe the structure of data types or the type or kind of a variable. But it's quite limited, and there's a set API. And that's a really good thing. And that's a big thing about this talk, is that it's not all negatives, even though that's all we see when stuff breaks. We don't see the good bits, but at the heart of template Haskell is a really, really nice design that allows us to work on this stable interface. And this is through dependency inversion, right? So template Haskell doesn't depend on GHC. GHC depends on the template Haskell interface. And this means that we aren't accessing GHC's syntax tree directly. Template Haskell has a copy of these data types. It does mean that there's some boilerplate in the background where we convert between these two data types from GHC's internal into template Haskell and from template Haskell to GHC's internal, but that's hidden from the user and is implemented in GHC. Also, the things we can know about stuff at compile time is specified by this quasi-type class. And again, it's allowing us to control what the user can do. This quasi-type class is instantiated by this Q monad, which you can think of like the equivalent of I/O. I/O is for running normal code, and Q is for running like meta programs. So let's take a look at an example of template Haskell in use. So here we are writing the normal hello world application in quite a convoluted way. So the stuff in the brackets, right? The stuff in the brackets is the template Haskell splice. That's run at compile time. So what we're doing here is we're saying we're constructing a syntax tree inside the quotes. The first part of it is print, which is a variable expression that's then applied to hello world lifted. Lifting turns something that is a string here into the syntax tree that corresponds to a string. So these are like a couple of bits of the template Haskell interface in action. And what happens when you run this is, well, when you compile it, is you get the print hello world example, and then when you run it, it prints hello world. So we can write meta programs. They manipulate syntax, and they can look at some compiler state, but not all. And we're not directly depending on GHC, which is very important for being able to separate things out. GHC depends on these interfaces. Yeah, there's some level of coupling with GHC because we have to do these conversions, and GHC actually has to implement these interfaces, but there's hope for like a stable future. Okay, so I'm just going to give, how are people feeling? That's just yeah, good.
Get your hands down so far, mostly.
That's good. Okay, now we're going to go into like the meat of this. We're going to talk about the specific interfaces of template Haskell. So when we're thinking about the interfaces, we can think about who the other party is, right? So one of them is going to be template Haskell. The other one might be the users, right? This is the main interface we would use. These are exposed through the template Haskell package, which is very confusingly named the same as template Haskell, the feature. And you normally, to enable use of template Haskell, you also have to enable language extensions. So that's also part of this bit of the interface. Then there's the GHC side of it, right? That's the implementation of the interface. And the interface itself is defined in GHC internal, and then the implementation is given in the depths of the compiler. And while now it's in GHC internal, it used to just be in the template Haskell package. So in the past, GHC depended directly on template Haskell, but now we have GHC internal, that is a dependency of GHC, and template Haskell that re-exports stuff from GHC internal. And finally, we have build systems, which in the past had lots of special behavior for template Haskell because of the complexities around its interface with GHC. But now that stuff has moved into GHC internal, we can just not worry about it as much. And what we really want from all of this is to make it easy to upgrade GHC and to upgrade template Haskell independently, right? These are two, we want to think about it as two interfaces that happen to be related, but really are independent. So you want to be able to upgrade your template Haskell package and everything still works. You want to be able to upgrade GHC, but keep template Haskell fixed and everything still works. Yeah, and as far as possible, we want that to happen. It's not really possible at the moment, but all of the suggestions for change are about making that a reality. And now, looking into the user-facing interface a bit more, we find that actually it's quite large, right? You've got these syntax trees, which are exposed by the library both as the data types themselves, and we also have a bunch of smart constructors for creating them. There's splices and type splices that allow, that are a piece of syntax that allow running code and inserting the program fragment from that code. We have typed quotes, which is syntax for representing some Haskell syntax as a syntax tree. We have quasi-quotes, which you can think of as a generalization of quotes. They allow you to write syntax that takes an arbitrary thing and turns it into an arbitrary value, depending on how the quasi-quote is implemented. We have the lift type class, which is about lifting stuff from runtime into compile time things, turning a value into the syntax tree representation of the value. And we have the quasi-type class, which has got a bunch of methods that expose effects that you can do while running splices. So you can make names, you can look up information, and then quite controversially, you can run I/O and stuff like that. There's also like some utilities around error handling and stuff like that. So these interfaces vary greatly in stability, and the main driver of the instability is their closeness to the syntax trees and how exposed you are to the nitty-gritty of syntax trees. Because the GHC syntax tree changes all the time. You expect that to change in every release as new features are added to the language. And because we want to have these conversions, right now, the template Haskell syntax trees also tend to change. But we'll see that we might be able to loosen that connection. And this variety of interfaces can be classified down into these four groups that vary in stability. So the most stable are what we call quote and splice clients. These only use splices, quotes, derived left, or quasi-quotes. So these clients don't really even need to depend on the template Haskell library in many cases. Syntax tree construction clients are very common, and that's what you get when you are creating type class instances, right? You want to insert some syntax tree, and you construct that programmatically using either these constructors or through the smart constructors in the lib module. We have reification clients, which look at compiler state, and this is also used in type class instance deriving. And then finally, you have like the least stable ones, which are syntax analysis clients that kind of want to look at the whole syntax tree and do a complete traversal of it. Maybe you're looking for like free variables or something like that. Because you're looking at everything, any change to the syntax tree, you're going to be exposed to it. So now we're going to look at these individually. Quote and splice clients, right? These are the actual features and what they look like. So we've got splices, as we've said, for inserting code. We've got quotes for creating code expressions from syntax. We've got quasi-quotes for arbitrary parsing. And we have derived lift for giving lift instances without actually writing any syntax trees. And all of these are quite stable. Quotes as a way to create syntax trees in particular are really nice because their stability relies on the stability of the surface language. One thing about the surface language is we really don't want to have a situation where one version of GHC parses something, but a future version doesn't. And we have quite strong guarantees about this in the GHC proposals process design documents. So we can piggyback on that. So if we have an expression, the quotation of that expression will also be valid Haskell. And because of that, we don't have to worry too much about these things breaking. Quasi-quotes are also quite stable. This is the entire interface of quasi-quotes, right? You've got different ways of converting strings into different types of syntax trees. And these will vary based on the context the quasi-quote appears in. So whether it's where it appears in expression position, pattern position, and so on, right? But most of the time, you really just have expression quasi-quoters. That's most of them, really. This definition, I don't think, has ever changed since the feature was added. Some library authors, like when writing definitions for these, might use the constructors directly or the library functions, which are a bit less stable. But in practice, most of them just create a value and then use a derived lift instance. So it falls into the same category most of the time. And that's for like writing quasi-quote or implementations. But when using them as a user, well, you don't care about that at all. And so usages of quasi-quotes are completely stable. Lift. Yes. Oh, yes.
The previous slide.
Yes.
Sorry, am I misunderstanding, or on the first point, isn't it foo parentheses quote x in the string, or am I just misunderstanding how they work?
That's a record selector, right? So you'll get the quote x. Yeah.
Thanks.
Yeah. It's a bit confusing. So yeah, as we've seen, lift is about lifting a value from one stage to the next. So you're turning a value into a syntax tree, and that's basically just boilerplate. You just write the value twice. This is also known as cross-stage persistence. And since most usages use derived lift, in practice it's all quite stable. But really, the derived lift usage is what's stable. Yeah. But these things, despite being quite stable, you still need to have the types in scope, right? If you want to give a derived instance of lift, you need to have the lift class in scope. And to do that, you have to import template Haskell. And while you'll basically never have to change your code to deal with breaking changes, you still will have to bump your upper bounds every time there's a new release of template Haskell. And that leads to quite a bit of churn. And it's completely unnecessary because your code's never going to actually break. So one step we're taking here is this GHC proposal 696 that splits out two sublibraries from template Haskell. So we have template Haskell lift, which is just the lift type class and some utilities. And then we have template Haskell quasi-quoter, which is just the quasi-quoter definition. And now users can depend on these directly and don't have to depend on template Haskell. So they're much less exposed to version bumps. And it also opens up a future where these libraries can evolve independently. So if we did have a breaking change, let's say to the lift type class, we could shim over that change in the template Haskell lift library. So you could have one version of it that supports one version of the interface, and the next major version of it supports a different major version. And you have some shims and CPP in the background to keep things working. And because the surface area of the package is much smaller, that's much easier to do. And there's another really nice benefit from this change, and that's it enables boot libraries to be dependencies of template Haskell. Right now, that's disallowed because boot libraries want to give lift instances, so they have to depend on template Haskell. So if we also had them as dependencies of template Haskell, we'd have a cycle. But by splitting things out like this, they only have to depend on the smaller template Haskell lift class. So now template Haskell can depend on them. And as we'll see in some of the future slides, that opens up. Yes?
So you can do this in user land?
Yes. Yeah. Well, the PR is ready, but I'm just waiting for the proposal to go through before publishing things in case people have thoughts about it. But yeah.
Like, the PR to what? Like, you just need to make some new packages and...
Yeah, well, right now they're going to be in the GHC repository, so that's the PR, is just adding them. And I also have draft PRs for all the boot libraries, so it's kind of like all in one place. But yeah, it's kind of like, it is quite ready to go. I just kind of have to release the packages to Hackage and stuff.
Yeah, because you could release packages now that depend on template Haskell, and then, or just GHC into
Yeah, that's exactly how it works. Like, there's a conditional where if template Haskell is older than something, it's, yeah.
And then they don't need to be in the GHC tree, which is...
Yeah,
depending on my boot libraries, then that becomes problematic.
Yeah, well, the future plan is to move it, all of them out into a different tree. So maybe template Haskell lives there as well, because it's just exploring stuff from GHC internal. But yeah, there's just minor things to figure out there, like how we want to structure it, but definitely doable. Okay, so yeah, pretty stable. We want to make this change to make them more stable, and then we won't have to worry about bounds. Syntax construction clients are kind of the really tricky case, because people use this stuff a lot, but it is quite unstable. So what are they, right? You want to create these syntax trees. You can use the constructors, right? So that's application. You're taking two expressions. You get back an expression. Then the smart constructors are all lifted into this quote monad, right? And it's just kind of a different variant of everything. And both tend to be somewhat unstable, although the library is less so. So let's take a look at a concrete example. In template Haskell 2.18, we had a change to the definition of constructor patterns. So right, that's when you're pattern matching on a constructor. So you have the name of the constructor, you have a list of type applications. Ooh, that's new. And you have a list of patterns for all the fields of the constructor. So the addition of this meant that a load of users had to change how they were defining things. So that you went from this foo and then a lot of things to this empty list because you didn't actually use this new feature. And users had to add CPP, wasn't very nice. In this case, the smart constructor also changed. But really, what we could have done is kept the smart constructor the same and then had a conp with type applications one. So there's opportunities for just doing these things better in the future. But if users, yeah? Somebody? No, okay. But if users are using the constructor itself, then it's very difficult to do it better with the current design. Yes?
It seems like these smart constructors are doing two things, because you want them to be a way of backward compatibility, but they are also doing this lead state to release A and in, which I'm not sure why it is. Like, what are they for? Like,
yeah,
why are these two aspects merged?
I think I think you're making a good point. And the question was about the smart constructors doing two things: backwards compatibility and this lifting stuff. And you're also unsure why the lifting stuff is necessary. Basically, because what quotes give you has this monad, right? Because when creating syntax trees, you want to have free variables, and the way that works is you have to have a monad to keep track of your free variable pool. So that's why you want everything to be monadic.
Applicative combinators are not that much noise.
Yeah, well, it's the choice they made when making the library.
Like that a long time ago.
Yeah.
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 Some people really like them for some reason.
Yeah.
It makes more natural sense to use the combinators like that, because then you combine with quotations as well.
Why couldn't
If you want to write, they do.
You can use them with monads, but yeah, it saves a bit of stuff. Yeah. Oh, yeah. Duncan?
So could you also have used like constructor patterns in it instead?
That's the next slide.
That's exactly my
They did not exist, definitely don't.
Sure, they did at this point.
They
Yeah.
have for at least 10 years.
Yeah. I think the issue here as well is that I don't think anybody's thought about this as a really big breaking change. And I think that's part of the change, is just thinking about that and finding out what stuff will break. Yeah?
There's a devil's advocate to that, which is once you've added those type parameters there, right? If you had a user that was previously traversing using that pattern, like thinking they got all constructors, and now they can't see all the ones that would fail that pattern match, because like those now have type applications, that user isn't served by that change, right? They just now have a partial.
No, but you could make an explicitly bidirectional pattern system. So when you match on it, you accept any list of types, and when you construct it or build it, you would use the empty list.
Yeah, so
But if you do that match, and you're using that as the only way that you actually got things, so you wrote code against the old conp, and now it's a pattern synonym, so it's going to miss half the cases.
But it's not, because
It will miss half the cases because those are the ones that happen to have type applications on them that didn't exist before.
But then
Now your code is partial, and there's no good way to describe the coverage
Well,
under the current.
this is all the next slide. Yeah, so there's how do we solve this, right? So this is actually, as we've seen from the discussion in the audience, this is like, there's a huge design space here, because we kind of want things to be more stable, but we also don't want to hide the fact that stuff is changing in the background. So one approach is to add stable field selectors and smart constructors for a specific version of Haskell, say Haskell 2010, right? And you're saying, with these smart constructors, I'm just constructing Haskell 2010. That's all I care about, and that should serve most users. That's something that could just be done now, right? That's purely blocked on somebody implementing it. And it's just a bit of boilerplate and legwork. So that'd be great if somebody felt compelled to do that. And then we could figure out if that's a good design and use it more extensively. Another thing would be to kind of extend that, and rather than just constructing these syntax trees using an older version or a fixed version of Haskell, we could also convert between them, right? You have like explicit conversion functions between the actual template Haskell ASTs and this other one. And then, there's some design questions there. How does that look? Is it failable, or do you have a maybe, something like that? And then another way of approaching this is have template Haskell ship a fixed syntax tree, but then you do the pattern synonyms, as we mentioned, to kind of gloss over the changes in the background. And it's a really tricky thing to figure out how that should work, right? Because once you bring in these pattern synonyms, there's some notion of, oh, now stuff's failable. Should we allow that? Should we change the way these syntax trees work and say, well, these are just open-ended types, and there's a constructor you can't match on in the background? Yeah?
There's one more tool that I just wanted to mention. Eric Mertens, when we were working on this with Lens for Make Optics or Make Lenses and all that, he wanted to build a library called TH Abstraction. I don't know if you're familiar with that.
Yes.
But with TH Abstraction, like in particular, you gave like A and B as like your most stable points, and C and D were your least stable points. And it covers largely C and D.
Yeah.
In an attempt to try and gloss over a multi-template Haskell version of like at least doing reflection on types and doing substitution on types. Because damn it, I don't really necessarily need to look at all of my types in detail as long as I can go through and substitute for names.
We will get to this when we talk about C and D. But the question was, can we do something like TH abstraction? And the answer will be yes. Yeah, so Adam Gundry worked on this last year and made some good progress. And I think one of the conclusions was that pattern synonyms are quite tricky and maybe aren't the best way to go. But really, we just need people to try these things out and put some more effort into figuring out what works. And all of these things can be done independently of template Haskell, because you can just have a package in front of it that depends on it, because these things aren't special. So yeah, another approach to solving this is to not do the syntax construction by hand, just use quotes. And I tried my hand at this with Esquelto, I think that's how you say it, this PR for that changed the law of the code, which used to be manual syntax construction, into using quotes. During that, I did find some bugs in quotes that made it a bit awkward to use, but now that we've found the bugs, we can fix them. And I think we should try this out with more libraries, because then we can make them more stable, we can find more bugs, we can make things better. So yeah, in this section, we've talked about the syntax tree construction stuff, how it's quite unstable. We could use quotes, or we could make some sort of shim on top to make them less unstable. Okay, so a little break. How are we feeling? Good? Okay. Yeah.
So what was Adam's, is Adam here? What was
Yes.
Adam's conclusion about the Shim package?
As Teo was saying, I think there's just lots of design choices here around how we can actually use that done. I mean, one thing I experimented with was basically using pattern synonyms for all the constructors. But pattern synonyms don't generate good documentation that way. Like things like complete pattern matching on types and things are tricky. So it's not quite clear what the right design is there.
Separate data type.
But I think something like separate data types with different views, like I can represent everything in Haskell 2010, or I can represent everything in GHC 2024 or whatever. I think something like that makes sense, but it does then mean that you need to introduce some call to a conversion function if you're creating a splicing and analyzing the abstraction. So yeah, there's still design work to be done there.
Yeah, so what Adam said was pattern synonyms had problems with documentation. Probably what we want to do is views over these things with conversion functions. So then C is reification clients. So reification is about looking at things, right? You want to look at what is this data type? What are its constructors? Are they strict? Looking for type class instances or type family instances or the types of variables. So you can actually get quite a lot of information about what's going on in the compiler from this. But a lot of these things return the same syntax tree types that we were talking about before. And this is this leads to the same sort of instability, but it's also a bit of an odd design choice, because the data the compiler is looking at isn't the surface syntax. It's a much reduced internal representation. And what we're getting back is a much more verbose thing. And then when you're looking at these things, you want to analyze them, and then you end up analyzing the surface syntax and redoing the job the compiler has already done. And the TH abstraction package does a lot of this for you and gives you back a much nicer, structured representation of a data type, and also exposes some other niceties. But basically, we should have that as the interface, and we could just do that, but that would be a huge breaking change to all of these users. So we don't want to do that right away. And part of the issue is you would think, okay, we have reify. Well, we can keep reify, and we add reify new. But that also breaks users, because this quasi class is exposed, and users can give instances of it. And users occasionally do that as like an MTL type of thing, where they have a state T with a Q in it, and then they give an instance of quasi. So it would break those users. So rather than doing it immediately, I have this GHC proposal 700 to split apart quasi into an internal and external interface. The internal interface is just seen by GHC, and we don't really care about it. And there we can add new things. And then the external interface is quasi, as is. And then in a future version of template Haskell, we can put out a new major version of template Haskell that is compatible with the same compiler. And the old version gives reify old, and the new version gives reify new. And you can upgrade template Haskell independently of GHC. So that will make it a much nicer transition. You had a question, Matt? No.
I always have a question if
Yeah.
you want.
No, I'm not going to push it. I just thought you lifted your hand and then put it back down.
That's his thing.
That's true. So yeah, we can decouple this, but a good first step is to figure out this interface for quasi, and yeah, just to make this a smoother transition. And then the last category is syntax analysis clients. And these are when you're kind of looking at the entire syntax tree. And a good example of why you'd want to do this is for variable substitution. So you kind of have to go through, look for all the variables. If the variable matches the one you want to substitute, you switch it out, right? And that's inherently unstable because you want to find all of the variables. If we add a new constructor to the syntax tree that has a variable field, you want to see it. So yeah, these types of clients are quite likely to break with every version because they want to completely pattern match on the syntax tree. And really, like, there's not that much we can do. If a user wants to do that, they want to do that. That's why we have complete pattern matching. But what we can do is look at why they're doing it and just do that in template Haskell or a different utility package. And that's kind of what happens in TH abstraction. But it also is something that happens in Lens. There's like 2 different implementations of variable substitution. So it's quite good to just move that into the template Haskell package, and that also makes it more discoverable, and we can document it and all of that. And yeah, being able to depend on containers from the previous proposal, 696, allows this to happen. Because when doing substitution, you really want to have a map of the variables you're substituting for good performance. Yes?
Isn't that overfitting, you think?
So the question was, isn't that overfitting a bit? I guess. I don't know. It depends on what you want from the library, right? You could be like, okay, this is just the interfaces. We don't want any utilities. But people write it. It could be in a different package if you want. But
No, but I mean, like, maybe there's something in between. Maybe you want to expose something like manipulate instances so that you
I
can
see.
do whatever you want without having to do the actual traversal. Instead of just saying, okay, well, here's the something.
yeah. So the question is, maybe we want some sort of like other method, uniplate type stuff. Yeah, that's possible as well. Yeah, go ahead.
Yeah, in response to that, that is something I've resorted to in the past. I just turned on orphan instances and derived lift and data for the entirety of template Haskell. The annoying part with that is there are some that are not going to be able to have default instances, especially the ones at the bottom of the tree. And your problem with that is now again you bump template Haskell, and now there's a few new constructors and things that you have to write new instances for. So, you're back to square one.
Yeah, so what was said is you can do that sort of thing, but it's tough, and then you meet other problems. By the way, one of the things you mentioned is that you wanted lift instances for all of the syntax tree types.
Yeah, that happened.
Yeah, that's happened. Yeah, that happened like last year. So yeah, and then now we're on to the last one, how build tools and template Haskell interact.
Sorry.
Yeah.
So B and D, so B and D are tiers, aren't they, in your tier list? But
Yeah.
the syntax construction, syntax inspection are surely related. Like if you have a Haskell 98
Yeah.
syntax tree,
Yeah.
then that's not going to change if someone is only interested in syntax analyzing Haskell 98 data types.
Yeah.
But many
Yeah.
people are interested in, but I suppose your point is that people are interested in working with any data type.
Yeah. So the question was, B and D are kind of related, right? And they are, but sometimes people do just want to construct syntax. But I think any solution to B will probably be a solution for D, but like a limited form of of a solution for B might just be a solution for B, right? You might think that it's a nicer interface just to have smart constructors and no conversion functions or something like that. Yeah. Okay, question back there?
Have you seen the Richard Eisenberg trick for unsafe coercing Q into TCM? What are your thoughts on that?
So the question was about coercing Q into TCM. TCM is the type checker monad. Well, that is just how Q is implemented, right? So I think it's unsafe perform IO, right? Well, not perform IO, but you're unsafe coercing. Rules don't apply. I don't really care about that.
Unsupported using.
Yeah.
What's the lowest key?
Yeah. Yeah. Right. Because like.
E for Eisenberg, yeah.
Because that's the thing as well. Like a big thing people have with template Haskell in general is like this running IO stuff, right? And Michael has a proposal to restrict that in some ways, but then you still have unsafe perform IO as a way of running IO, and that's really difficult to get away from without hamstringing the language. So for build tools, it's had special treatment in Cabal Stack and Hadrian. Hadrian's GHC's internal build tool. And really, they're not required anymore because all of the magical wired in stuff has moved on to GHC internal. But build tools don't know that. And in particular, Cabal install and Stack will refuse to install a different version of template Haskell to what was provided. And there is actually an undocumented, I think, or I haven't found the documentation, flag for Cabal that allows boot library library installs is what it's called. And that allows you to actually do this, but that's quite awkward. And so we have a ticket to teach Cabal install about this, which is a collaboration with Matthew Pickering. And it's mostly ready to go. I think we're going to finish it this weekend, probably. And that'll allow reinstalling template Haskell. But there's a further issue. You had a question?
I just had
yeah.
We're talking about build system integration.
Yeah.
A standing issue that I think has been rotting on template Haskell for a very long time is the add-dependent file doesn't get reported out to Cabal in any meaningful way.
Yeah.
So it doesn't actually use it. So if you use inline C, PV, etc.
Yeah. So the question is about add-dependent file not being known by Cabal, and that's kind of just Cabal doesn't know about G. Yeah, that's kind of orthogonal to this stuff, but yeah, it would be good to solve it. Yeah. Yeah.
Just gotta let it out sometimes, haven't you?
Yeah, it's. We just need some sort of interface to say these are the files, because Stack can do it by looking at internals, which isn't good. And then there's another issue though, right? If we solve the one from the previous slide, it's actually still quite difficult to reinstall these things because Cabal has this behavior where it doesn't like to reinstall what are known as global packages, which in practice are the ones that come with GHC. And that's kind of a leftover from where Cabal version 1, where you had a lot more control over these things. But kind of what happens is, unless you have a constraint explicitly forbidding it, or there's no valid build plan, it will just use these even if there's a newer version. And this is quite confusing and it's not very nice. And there's this issue about it. And kind of the conclusion from it is we don't want to change the default, but we do want to add an option to enable just picking the latest. And I think this would be a really good newcomer project to Cabal because there is an older PR that does the same thing for allowing picking the oldest in all cases. And it's a very similar change. It's got tests. You can just kind of take that and just tweak some things, I think. And you should probably have something that solves this quite easily. And it would be really nice. It's not only a template Haskell thing as well. It's just annoying for boot libraries in general. So yeah, in terms of build tools, they're just kind of lagging behind GHC at this point. And we just need to finish off teaching them about how template Haskell has changed. And now to conclude, right? Template Haskell is this really large surface area, and the syntax tree is this thing that runs throughout it. And by separating out the stable parts and being explicit about that, we can benefit from that stability. We can work on improvements, And by and large, it's by adding some distance from these internal things, making stuff more abstract, reducing the tight coupling between these systems. And yeah, we have potential for a really nice, stable template Haskell. And as you've seen from the talk, there's like a bunch of things that you can get involved in and help out with. And it's very simple Haskell work a lot of the time, just defining data types, figuring out interfaces. So yeah, do get involved. Thank you. And that's the end. Do you have some more questions? Do you have time for questions?
Yes, you have time.
Okay. Matt, and then
No questions. No.
yeah.
I personally like the idea of having like Haskell 2010 data type, template Haskell 2010, and that's just a different data type which doesn't change, and there's conversion functions from that to the GHC version.
Yeah.
But I'm not writing template Haskell code typically. That just seems the nicest thing to me.
Yeah.
So that is comment, not question.
Yeah, and I think there as well, like one potential issue with that is we've moved past that with template Haskell. So if people wanted to switch to that, they'd actually have to change all of their stuff again, right? So maybe what's better is just template Haskell 2025 and just take the current AST as that starting point, maybe.
Yeah, yeah, good point.
Yeah, like that, yeah?
Yeah. So I've come across in the GHC source tree, it defines some custom folds for expressions and types. Would that be something that, like, custom folds because they need to be binder aware and all that kind of stuff? Could that be useful in the C group, I think you called it?
Yeah, maybe.
As
Yeah.
more general than just variable substitution, more general.
I see, yeah. Yeah, yeah, I think so, yeah. I'm not really sure what in particular you're talking about. Maybe you show me later. Question mark.
So if I correctly, template Haskell is now decoupled a little bit from GHC, but it still has such a large surface
Yeah.
that it will probably still have frequent major releases, right?
Yeah.
So then you talked about other tooling like this TH abstraction stuff,
Yeah.
or iterating about various substitutions and stuff like that. Wouldn't it be moving that into template Haskell doesn't make a lot of sense then to me? Wouldn't you also want those interfaces to be more stable and that live outside, and they just are another layer over template Haskell, exactly like the template Haskell lift technology?
Yeah.
Just for another use case?
Yeah, so the question was basically, should we, if adding utilities to template Haskell, maybe we want that to be a separate package, which can have a more stable interface. Yeah, I think you're right. I think kind of one thing I think was unspoken is that maybe we want to remove the ASTs from template Haskell, right? Yeah, actually, maybe we don't. Like, that's something we keep going back and forth about in these discussions. It's like, oh, do we want to take the ASTs out and then template Haskell is stable? Or is template Haskell the unstable thing and we want other stable things? Adam?
Yeah, I think there's a genuine tension here because template Haskell, its current API, is not very well documented and it's got lots of stuff in it that we don't want to keep the way it is. But then do we try to change it and break every 1 month? Or do we try to come up with a new package that does things better and persuade people to migrate to that new package? So
Yeah.
I'm not quite sure what the right way to address that trade-off.
Yeah, so there's a tension between breaking everything at once and then we have a nice new API, or creating new ones that we encourage people to switch to. Michael?
Just worth noting that template Haskell being in, say, the GHC source tree has an implicit social advantage in that people assume that it will get updated
Yes.
and kept working
Yeah.
immediately on new GHC releases, whereas, Teo's TH utils, maybe
Yeah.
on holiday.
Yeah, it's a worry, right? So it's like having it in the GHC source repo makes people more secure about it. Yeah.
What's the best way to test and debug template Haskell?
That's a really good question. So what's the best way to test and debug template Haskell? I'm not really sure because it's quite annoying to do it in GHCI. I just end up having like a file with something in it, and then like printing things and doing trace style debugging. But yeah, maybe somebody else has a better answer to that than me. Yeah.
All right. The lack of an answer is a good answer.
Yeah.
All right, well, let's thank Teo for that.